Good morning, everyone. A warm welcome from the Department of Physics, Willingdon College, Sangli. 2025 is the International Year of Quantum Science and Technology. To celebrate this, we have organized a real competition and webinar on quantum computing. Nowadays, AI and quantum computing are the next two essential. This opens up a large number of career opportunities. To make aware of this, we have Mr. Sangram Deshpande with us. I would like to call Mr. Ivan Kulkarni sir to introduce him.
Thank you, Shreyashi. It's my pleasure to introduce Mr. Sangram Deshpande. He is from Maharashtra itself, India, and he has done his bachelor's in computer engineering, and he was very fond of quantum computing from those days. Also, I have seen his progress so far, and now currently he is working as a research scholar at North Carolina State University, USA. So I will not talk much of about him. He will introduce in details about himself. I will give more time to him, and I will like to tell you all people from India that for this webinar more than 200. Recently I saw it is above 250 participants have registered, and Sangram is joined from USA. There is a night there, so he is sparing night time with us. So let's make very good out of it. Thank you. Now over to you, Sangram. You can start over.
Yeah. Okay. Yes. Mm, just a second. Let me share my screen.
Okay.
Wait a second. Yes, I hope my screen is visible to you now.
Yes.
Let me know if it's having any problem. Okay.
Yes. Yes. Your screen is visible.
So let's start.
Yes. Yes.
Let's
Sure.
start with quantum computing.
Sure.
Sorry for a little delay. Mm, the So, like, first of all, as Eugen told that, I mean, I and Eugen were friends. I mean, where means we are still friends, but we spent little like time together at Shivaji University, Kolhapur. I guess around 2017 to 2020. I graduated in 2020 from the KID's College of Engineering, Kolhapur, and I used to like go to uh, physics department in Shivaji University for this quantum, like understanding quantum. That time I was very, I mean, still I don't understand quantum mechanics, but I mean, I wanted to like learn that time, and I spent my most of time in there only. So yeah, okay, let's start with quantum computing. So I have given, yeah, and another thing that like like we have organized this talk for in the occasion of International Year of Quantum Science and Technology, right? So, I mean, there is a reason why we are celebrating 2025 only as a uh, International Year of Quantum Science and Technology. Why not 2024 or 26, right? So, the profound foundations of quantum mechanics was built in 1925 by Heisenberg, then by Niels Bohr and Schrodinger, on during that time only, and that's why we call, I mean, we preferably say that 1925 was the year of quantum mechanics, where quantum was developed in actual sense, the way we are using it today. In 1900 only, Max Planck gave quantum theory, but to the actual realization of quantum mechanics was happened in 1925. So that's like we are completing 100 years of quantum mechanics, or actual quantum physics in that sense. Then that's why we are celebrating 2025 as a year of uh, International Year of Quantum Science and Technology, right? So I have given here a note that it's a welcome to the future, right? I mean, I'm not taking you anywhere in the future, or I'm not talking about the fantasy or sci-fi stories, something like that. But it's the future of computing. Okay, so let's start with the computers. Okay, so basically, whatever we use today, laptops, desktop, whatever. Okay, even calculator, mobile phones are all are all computers. And when we talk about when we talk about the quantum computation, we call this as a classical computers because it works on the law of classical physics, like thermodynamics and the like uh, classical heat equations and all. Okay, I mean it all comes under the classical physics, right? Uh, so like this is the computers we are using today is called as, I mean, we can call them as classical computers. So basically, history of computers begins in the year of 1940s, right? That time during the World War II, people were developing different computing machines to compute the large equations in physics. If you have seen the movie of Oppenheimer, the atomic bombs calculation was very hard to buy manually, and that's why people start feeling that we need computing machines. I mean, I won't call it as computers, but those were computing machines, right? And the history date back to that time. So as we all know that we then moved to vacuum tubes, then then transit, and then we came at transistor point, right? Today, still we are using transistor, but the size of transistor is went to so small. I mean, so small scale that on if you see our current Android phones have transistor of 7 nanometer size, right? And I guess all you must be knowing the what's the significance of nano level, right? So once we go beyond nano level, we go in the subatomic physics. Or in other words, I would say that today's current transistor size is of just 100 to 1000 atoms wide. So you can say you can imagine one transistor is having size of just 1000 uh, atoms, I would say. So if we go down by, and there is another Moore's law, so which basically states that from the 90, it was stated in the early 1970s. So that states that the law states that the transistor size will double every year, and uh, the size will sorry, the number of transistors on that same area would be doubled, and the obviously the size would be reduced by 2 times. And now it's even if we see it linearly, we are coming to the kind of limitation of classical physics. Now we are already at the nano level, and once we go beyond that, we will need to like treat an electron as a transistor, right? So, or like one single atom as a transistor. So these are the like limitations of classical computing machines, and that's why we have. Uh, I mean, that is one of the reason why people started looking into quantum computation. And there are other paradigms to bypass Moore's law, like neuromorphic computing and some like those are kind of abstraction, uh, like abstracted ways of computing. But I mean, today's topic is quantum, so I would stick to quantum. So I think most of you are from physics background or like have some sense of physics. So I would not like I would make it more technical towards physics, not towards computing. So as you can see, like the first image I have given is of superposition, right? So basically, Schrodinger formulated this thought experiment that until and unless like someone observes that particular state, one should not be knowing that if the cat is dead or alive, right? And I'll tell you the uh, I mean another significance of this into other experiment. So this is the superposition principle. The equation you are seeing here, the equation you are seeing here is of uh, the Schrodinger's equation, which is basically a equation which used to calculate the probability of an electron, like probability of finding an electron in that particular orbital, right? So yeah, another thing I have given here is the quantum is probabilistic, and we'll see how it actually helps us in computation. So on the left hand side, if you see, there is a wave. I mean, there is a double slit experiment. You must have like seen that. So yeah, okay. So if you see, we place a detector there, and that's why I mean, when we place detector, we do not get this waveform like this. When we do not have a detector there, then we get fringes like the interference pattern like this. Okay, and the another principle is of quantum tunneling. Actually, this is a simple demonstration of quantum tunneling. Basically, when an electron has to like cross the energy barrier, it just tunnels through it. It doesn't like climbs the all the like hill and goes to the other side. It just tunnels, and it that's why we say that quantum is amazing or nobody understands quantum mechanics because we do not know like why this happens. And there is another principle called as entanglement. So entanglement is basically uh, the two particles are mathematically are close together. We demand that T maths for quantum mechanics. Quantum mechanics. And if you see, the Nobel Prize in 2022 was given to in physics was awarded to three physicists, and the work they have done was basically demonstration of this entanglement principle. Okay, Einstein called this as a spooky action at a distance. Even Einstein, as a like great physicist, was uh, in the opinion that nature would not do such spooky things. Rather, it would be more deterministic in nature. But Einstein's collaborators only EPR, Einstein, Podolsky, and Rosen have uh, given this theory, and Bell, it, uh, the John Stewart Bell in 1970 gave mathematics for that foundation of entanglement, and that uh, entanglement was carried out by three physicists. They got that they kind of demonstrated that entanglement is really happening in the world, and I mean in the universe, and uh, Einstein, like there is still spooky action at a distance. And if you see, this is a simple quantum circuit. We will come to that point. But it's I mean theoretically entanglement is basically if two particles are at two distant corners of the universe, still action on like operating on one would give us the result of the other one. Okay, so we can like define entanglement like that. I mean, though I'm not like physicist, so I won't be able to um, explain a textbook definition of entanglement, but this is what I have understood. And uh, if you see the circuit here is basically showing that these two qubits are entangled. Okay, and in the other image, if you see teleportation seen some animated movies like Hollywood animated movies in that they have given teleportation concept, right? So, but here we are not teleporting an object, but we are teleporting a uh, quantum information, or we would say quantum state. Okay, quantum state of one qubit would be teleported to the other qubit, which is far at a distance. Far at a distance. Okay. Now we will come to qubit, uh, like qubit state. So basically, uh, on the right hand side, if you see the bit difference between bit and qubit is given. So it's basically uh, classical bits are either 0 or 1, right? But qubits are 0 and 1 at the same time. It can be either 0, it can be either 1, or it can be 0 and 1 at the same time. It's called superposition, right? So the representation of qubit is called as the block sphere, and I mean it's basically a mathematical representation of qubit. Like it's nothing complex, but we use complex numbers to demonstrate this block sphere. And the z it's like divided into three axes, x, y, and z, and basically we require to shift uh, the rotation of the qubit should be happening in such a way that the our expected outcome, or like I would say it as an algorithm. Okay, it should be we are applying quantum algorithm on the qubits, and qubit states uh, uh, are getting like transformed into some other state, same qubit with the other state. Okay, and this is the like yeah, this is pure mathematics of the quantum states. Yeah, and then uh, superposition uh, the exponential power in one qubit. If I would say you that if I'm having 10 qubits, I can, hello,
கிளாஸ் நம்ம அப்படி ப்ராப்ளம் போட்டு போட்டு ஆன்சர் சொல்லிட்டே இருக்கோம்.
hello, am I audible? Hello, you can.
Yes, you are audible.
Okay, I heard some noise, so very clear. So yeah, I was just saying that mm, yeah, we have to apply quantum algorithms to get some output. Okay, yeah, and we get the exponential power because of the superposition. Because in just 10 qubits, we can have the 2 to the power 10 classic, the power of 2 to the 2 power 10 classical bits. And if we just increase this number to the power, if we go more than 2 to the power 50, we have that number which which is like very high number, and uh, I guess 2 to the power 53 is the total number of atoms in the visible universe. So it's beyond that. If we go like 2 to the power 100, then it would be beyond like our classical computation reach. So here it comes to the bridging the to quantum algorithms. How we are like uh, till now we have saw the um, qubits and it's like mathematics, and now we are coming to quantum algorithms. So we have to apply these qubits to the actual scenario, some solving some problems, right? What computer does? Computer solves the problem. So we are basically our aim is to evolve the qubit state to the solution state, and for that we require quantum gates. So here you are seeing few quantum gates are like single qubit gates and two qubit gates. Basically there are like multiple qubit gates as well, but we can visualize these two gates for now. So Hadamard gate is basically the superposition of the states. It actually see at the end everything is mathematics. Okay, it's like it's mathematics only. It's vectors, and we are creating a superposition of the first qubit, second qubit, and then we are connecting those two qubits with the third and then fourth qubit. If you see here, and then we are measuring the first qubit. So, uh, and another thing is like, have you imagined that uh, a quantum chip would be of size of like just uh, like few millimeters. I mean, I would say 1 centimeter by 1 centimeter. That that's a high, like biggest quantum chip like existing in the world. So to operate the, I mean to apply the like the problem on that such small scale quantum chips, we would need some control mechanism, right? And we control that qubit using the microcontrollers. And we need zero pressure. I mean, not absolute zero, but 15 millikelvin temperature, just slightly above the absolute zero to make the uh, qubits working on the quantum nature. If we increase the or like if those qubit gets the thermal radiation or some other radiation, other form of radiation, those would be decohered, and those will like, lose the quantum nature of the qubits, and those will be essentially then be a classical qubits, sorry, classical bits only then. Now for quantum algorithms, like I have like these are like if even if we start teaching one quantum algorithm, it will take like more than half an hour. So I won't take uh, depth into that, but I'll just like tell you the, I mean, importance of these algorithms. You can then go on and study this algorithm if you find interest in the quantum computing. You can start with these basic algorithms, and then there are like many algorithms which are being used today quantum advantage, theoretical quantum advantage. We are yet to have the quantum computer machine which is like capable of uh, giving the quantum advantage. Okay, so basically this Bell circuit is a simple demonstration of entanglement. We are entangling cube zeros and first qubit, and we are measuring in it in the third state. Okay, so it's Hadamard gate and it's CNOT gate. You will learn about these gates once you start like taking into quantum computing more. Then there is a Grover's algorithm. Okay, so basically Grover's algorithm gives us benefit that it can, yeah, mm, second, yeah, Grover's algorithm can find the uh, and search from the like unbounded in so if we have 1,000 um, elements in an array, then classical search would need 1,000 maximum 1,000 attempts to like search for that particular element. But Grover's algorithm would need root like square root of 1,000 only. This much attempts to get to that particular element. Uh, it's Grover's basically used in the searching. Then there is Shor's algorithm. You might have heard about this Shor's algorithm. Basically, Shor's algorithm is a factorization algorithm. There is are all the encryption algorithms which we are using today are based on the uh, classic prime number factorization. So if we have two big prime numbers and if we like multiply them, it would be hard for any hacker to split that big number into two and that basically our entire encryption system is based. Our banking algorithms are encryption used in banks and all that is based on that. And Shor's algorithm theoretically claims that we can uh, solve that prime factorization problem within few seconds. Let's say if we have a big prime number, then we can factor it into it two it it's two factors in very small amount of time, like just few seconds or like less than few seconds. If we have the uh, 10,000 qubits machine, then we could do that, and that's where the exponential power of quantum computation plays in. And uh, if somebody from this talk is like from mathematics or is having interest in mathematics or computing theory, then it would be like more interesting to him or her. That there is a generation of two
स्क्रीन
categories
किती शेअर आहे.
of one polynomial. So basically, uh, polynomial are the algorithms which could be solved by classical computer, by today's classical computers, and non-polynomial are the ones which cannot be. I mean, it's a simple definition, I would say. But quantum computers are capable of solving these non-polynomial algorithms as well. Basically, polynomial means we know for that particular problem that our classical computer could solve that problem in a finite time. It won't take infinite time. But non-polynomial, we theoretically say that it's going to take infinite time. But quantum computer would be able to solve this non-polynomial algorithms in very small amount of time, like less than few seconds. So now hear more about quantum algorithms. There are these quantum algorithms shows actual quantum advantage on today's quantum computers, like 100 qubit or like 1,000 qubit quantum computers. We have at maximum of 5,000 qubit machine. So we can uh, prepare quantum states, then we uh, run it through the quantum chip, I mean actual quantum processor, and then we parameter, then we optimize its parameters. Okay, using classical model. That's why we call it as a hybrid quantum algorithm. And um, because of this, we get better accuracy, better solution. I mean, optimal uh, solution in lesser time, and also uh, when we like scale for the more than 1,000 variables, our classical computers do not work for some particular problems. But quantum computers for 1,000, for 10,000 variables as well, it works pretty fine, and it has power to uh, surpass the classical supercomputers as well. So there is another one is quantum annealing. I would say the quantum computing hardware technologies in a moment. And so basically, this quantum annealing is a paradigm of is another paradigm of computation, and it basically we simulate a Hamiltonian and we evolve it over the time period, and these are the qubit technologies. So basically, the most widely accepted and widely like popular, I would say, quantum computing technology is a superconducting qubits. It's basically a like electric circuits. It's actually not. It does not work on the actual atom or like atomic level, but it creates a quantum effect using the inductors and using some electrical circuits. Okay. Then there is another one. If you're seeing it at the right top of the slide, there is a trapped ion quantum computer machine. Uh, it's actually this machine is even smaller than like 1 and there are I guess 40 or 50 qubits are placed in line on that like straight line of that chip. Okay, so that's called trapped ion. Basically, create ions and we trap them uh, inside the using some particular approach, and that's called trapped ion quantum computing. Then photonics, if you see here, photonics is basically a laser based quantum computation. We create photons, as photons are basically inherently quantum in nature. So we utilize those photons, coherent photons, and we apply some uh, operation. We apply some different operators on that to create that particular pattern, what like the one we wanted. Then there is neutral atoms quantum computing. We create this neutral atoms quantum computing using bit precision, and it's like that atoms is created, and then it's like interacted with the coherent laser pulses, and that's how we get a single qubit, or we can say this single atom acts as a single qubit. Okay. Then there are applications of quantum computing. Hello, Jugen, may I continue?
Yes, yes, Sangram, you
Yes, sir.
continue.
Yes.
Yeah, 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 sure, sure. Yeah, then there are like applications of quantum computing. So basically, people are not like mad that they would like they are putting millions of billions of dollars on this quantum computing technology. They are seeing some advantage out of it. That's why people are putting their money, right? So basically, the applications are involved in drug discovery, then finance. I mean, still today's uh, classical computers are not, or even supercomputers are not able to simulate supercomputer is able to just produce the just simulate the molecule which is of like 50 electron-electron interaction. If we go beyond more than 50 electron-electron interaction, classical supercomputers also fails. So that in that domain, quantum would be highly useful. Then in communications, because of entanglement, that's another topic. If you want like learn about that, you can learn independently, or you can or like we can have another session on quantum communications only. Then there is quantum chemistry, as I said, the uh, the interaction of or the reactions of molecular reactions we can simulate using quantum computation. Then there is quantum key distribution. Then there are real world applications in optimization problems. Drug discovery is another, we can model it as another way of problem solving. Climate modeling, simulations, financial modeling. Today, uh, if you have seen the financial models, those are very complex. Weather models and financial models too are very complex, and those are like we have lots of data available of it, and really a supercomputer would also fail to simulate that properly. And then there are like machine learning and AI. Obviously, there are like I guess by now there are around like 150 to 200 companies working in quantum computing domain. They're like big big industry players like IBM, Google, then Amazon, AWS. These are like big players, and there are like other companies as well, which are working on the quantum algorithms, or which are working on the applications of quantum computing. Then there are few other companies which are working on the development of quantum hardware. So we have saw like three, four, like those are uh, like essentially most popular, like most quantum technologies. Uh, and scholars Rigetti are working on the superconducting qubits. Then there is D-Wave, which is working on quantum annealing. Then there is, Xanadu, which is working on photonic-based quantum computers. Then there is IonQ, which is working on ion trap quantum computing. There is Quera, which is working on neutral atom quantum computation. And there are like many companies working on uh, like different aspects of quantum computing. So if you see here on the left hand side, there are few companies listed as user. So JP Morgan, then Wells Fargo, these are banks uh, are utilizing quantum computer for their applications. Then this is like AstraZeneca is working on quantum computation for drug discovery, molecule simulation, reaction simulations, and all. And there is Airbus is working on material science. Then there is BMW, uh, it's working on the for as their there there are actual people are like realizing the quantum advantages, and that's why people are more embarking towards the quantum computers. So, like in recent past years, uh, like this has been 100 years of quantum mechanics. Quantum actual for formalism of quantum theory, right? So, in these 100 years, we have crossed a long way, and I would say that like in recent like last 5 or 10 years, we have we have started developing the actual quantum hardware. Sorry, yeah. So
Not
you might
our
have hello. You might have saw uh, the news from Google that they have demonstrated the quantum below chip, and it's they have claiming supremacy, and they are and the the quantum computer goes below chip was unprecedented, and no classical computer would be able to solve that for the 10 to the power 7 years. 10 to the power 7, 10 septillion years. Mm. So these are like claims people are making in quantum domain. And as I have said already, BMW is already using this for optimization. HSBC is using in banking. And so like whatever we can conclude from this is quantum is very near. Like we would have scalable quantum devices in the like next probably 10 years, and by that time we would be like all the crypto systems would be broken. Then it's not a threat. People are working towards quantum safe cryptography as well. That's another like point of discussion. But yeah, that's what like power of quantum computing lies, and what threats, what advantages it has. And now, so that India is not like uh, India is also working towards quantum, and India just in 2023 launched National Quantum Mission. It's a 8 years roadmap. So India's aim for this National Quantum Mission is basically to develop in-house capability, in-house quantum chip of like 100 qubits. So basically, we can scale it up to like thousands or like 10,000 qubits by the end of some 20 years, let's say from now onwards, and we would be uh, we would have no problem to worry about the quantum threats from the other countries. Like China has demonstrated quantum communication in 2017 only. So by taking that into consideration, China can hack our channel, but they won't be able to hack China. That means communication is free. So that's why India is working towards the uh, in-house capability of quantum computation and development of quantum hardware chips. Then India is again not only developing it for India, but India wants to like commercialize the quantum computation as well. Then one of the important aspect of national quantum mission is utilization of quantum computation for the quantum communications, exactly the quantum satellites and basically secure quantum communications. Then apply this in industry. If we like develop chips, in-house chips, we would be able to create startups from India, and we would be able to use our made in India quantum chips. That's 8 years roadmap. It's included in their 8 years roadmap. And yeah, opportunity for startups, opportunity startup there in different hospitals. One of them, which is very close to us, is either Pune. And
तो काय
either
म्हणता
Pune Quantum iHub is giving
मराठी जरा
guidance
वेगळंच आहे.
to the ones who are interested to learn about quantum computing, those who are interested to like start some startup or start some project in quantum computation. They are giving funding for that. They are giving guidance for that. They have very experienced professors working in that. And another and most important aspect of National Quantum Mission is to develop more startup culture in quantum computation domain within India. So, we all have said about uh, we all know about the quantum computation, how it's going to affect us, what India is doing, but how we can develop our skill set to match to that particular required skills in the quantum domain. Okay. So the navigate quantum so we have to get national quantum missions. Uh, Another milestone is to develop skilled workforce in-house and deploy it on the India's National Quantum Mission challenge, different projects. Okay, and another problem in quantum computation is there are very few skilled people in the in the quantum domain. In India, there including IIT professors and all, there are less than 1,000 or like less than 2,000 people who are actually working in quantum computing and who are developing something towards the quantum computation, towards the better future of quantum computing. And yeah, so there is high potential chance of creating ample of opportunities for students like you guys. The only requirement is you have to like skilled in physics, obviously in
नंबर वाढला बघा
industry
अटेंडन्स.
mathematics, and you have to best in linear algebra. Then it comes to the computer. You have to understand coding, then algorithms, and these are the like basic requirements. And the machine learning and high performance computing are the later on stages. So you can grab opportunities for getting fully funded PhD opportunities within NQM or even outside India. Like most of the globally people are working towards quantum computation, and Europe has given some uh, I guess $1,000 billion or something around that. They have given. Only Germany is putting like big amount of money into their uh, Munich Quantum Valley project, and obviously US is putting lots of money. But apart from all this, you will get you will definitely get some opportunities in the quantum mechanics. Okay. So coming to this point, bonus learning. Uh, I have pasted one photo from the. It's a letter from Ramanujan to G.H. Hardy, his professor at Cambridge. So, I mean, it's little out of topic, but I really wanted to like tell you guys this thing that what if Ramanujan haven't post like if he never posted this letter to Hardy, what would have happened? The world would never be able to know the uh, work of Ramanujan and the potential of Ramanujan, right? We would have missed this legend mathematician. So, like, if you are failing, and he was self-taught, right? Every like all of us knows the Ramanujan's story. He was self-taught. He was working as a clerk in that Madras Port Trust, and out of his that time, spare time, he was giving to learning mathematics. Both he is an mathematician. What can we learn from this? Uh, if you believe that your application, or like if you believe that you should approach to one particular professor or like one particular uh, domain, then go for it. Just don't think and go for it. Write 100 letters, go for best, and there is always a probability of 50-50%, right? Probability, I connect this probability to quantum mechanics again. There is always a probability of 50% dead and 50% alive, right? So, like, there is always 50% chance of getting selected and 50% not. If you don't try, then it would be zero only. But if you try, the 50 would be converted to 100. So that's the potential benefit of, I would say, understanding quantum mechanics and probability theory. So yeah, I mean that's what, like, from my side, the learning resources and takeaways. You are like free to read quantum mechanics books, quantum books, ton of books on online internet. Even we have the it's kind of a Excel sheet which has all the resources for learning quantum computation. It has books, links to the books. You can freely download it. You can even ask to me. And the and the main takeaways are basically learn about quantum computing, not only about quantum computer science and physics, but learn around of these concepts. Then just now we discussed the probability theory. Always remember that work on real world projects. You will get lots of projects in the GitHub. You can just try to like go through it and you will understand the coding of it. It's not that hard. And if you want to pursue career in quantum, just start now. This is the right time. Okay. Now I guess we will move to the questions. And I guess this, okay, sorry. This is, sorry, this is like it's called like, if you want to see sangram1563@gmail.com, and you can connect with me on LinkedIn. Okay. Yeah. Yugen, I'm done from my side. If there are any questions, I'm happy to answer.
Thank you, sir. If anyone have a question, then unmute your mic and ask question.
Sangram, this is Raghavendra here.
Okay. Hi. Hi,
Hi.
Ravindra.
I just wanted to ask about see how a real life or how a real world problem is
Mm-hmm.
converted into this quantum logic or quantum circuit, or how
Mm-hmm.
how you how you kind of convert
Yeah,
that and
breach
find the
that.
root.
Yeah, breach that. Yeah,
Yeah,
okay.
yeah,
So yeah, we had saw just let tell I mean briefly answer that question, and then I'll demonstrate something for you. Okay. Mm, just see. Mm, like tell me, are you from chemistry or like do you understand chemistry or do you understand optimization better?
yeah. I'm from a computer background.
Okay, computer. Then great. So basically, what we do is uh, we convert this problem into optimization. I mean, I'm talking about optimization. It's one of the problem we can solve it on quantum computers. We convert this optimization problem to the quantum Hamiltonian. Okay, and we then evolve evolve that problem Hamiltonian to the solution Hamiltonian by different quantum algorithms. Like one I have told is VQE, variable quantum eigensolver. Then there is quantum approximate optimization algorithm, that's QAOA, which is similar to VQE. And there is quantum annealing, which is inherently associated with quantum computing. And we use parameters or variables on the uh, in terms of the qubit mappings. And if we, this is about quantum annealing and superconducting qubits. If we go on neutral atom quantum computing, we just have to like convert our problem statement into the uh, like a graph which depicts uh, the graph. We have to convert that particular problem to the similar structures our qubits are having in that in that topology. Okay, so once we are able to convert that uh, problem into the particular qubit mappings, we just have to like done that. We just have to like run through that computation, and then we get output. And obviously, as said, it's a probabilistic I mean, quantum mechanics itself is a probabilistic. We run it for like couple of like thousand times, and then we like sample it based on our best average case. So that's how we get the better accuracy and uh, like within the less resources. I would say fast, then better accuracy and all these terms. So, I mean, this was a really nice question because if we don't know how to connect or how to bridge these two things, then it would be of no use, right?
Yeah, agreed. Thanks, Sangram.
Hmm. Yeah. Are there any more questions?
Hello, Sangram. Am I audible?
Yes, 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 yes.
Yeah. This is
You're
Bipin
audible.
Sonawane. Yeah, this is Bipin Sonawane.
Mm-hmm.
So
Okay.
yeah, there is a question like,
Mm-hmm.
see, people
Mm-hmm.
need to understand basics of quantum mechanics to
Mm-hmm.
understand quantum computing.
Okay. Mm-hmm.
So yeah,
Right.
I'm teaching quantum mechanics as well as BTech students. So BTech
Okay.
students are trying to understand this quantum computing without understanding quantum mechanics. So there might be some struggle to get into the details of
Mm-hmm.
quantum computation. So
Okay.
technically or maybe academically there are some loops in this field I found.
Mm-hmm. Right.
So do
Right.
you find any kind of solutions in this?
Mm-hmm. Okay, so as you can introduce me that I'm a computer science engineer. I'm not a physicist or like I haven't studied. I haven't taken formal class of any physics, not quantum mechanics, not quantum physics. Whatever like I have learned is on like self. I'm kind of like self-taught in quantum physics, quantum mechanics. So I mean, you are right that quantum mechanics is pretty vast, and we need to like, and we need to know quantum mechanics to apply it into the quantum computation. But in the other words, I mean, I would just express my thought. I don't know if those are like I mean, state of the art or not. But the way I have used is, uh, I never like try to first learn the quantum mechanics or quantum computation. What I did is, I I studied quantum computation, one particular concept from the quantum computation, and then I visited quantum mechanics to understand that part pretty clearly and in a better sense. And this was the way I have used. I never tried to understand full quantum mechanics in one go, or first understanding quantum mechanics and then going for quantum computation. But I always prefer that understanding it parallelly would benefit me more. And I guess this is the, I mean, uh, way I did. I do not know that if it's the state of the art or if it was the best way or not, but it proved best for me.
Okay, okay, that's good.
Yeah,
That's good. Sir. So this is one of the solutions to go ahead. Yeah.
yeah,
Okay, fine. But at the end, see, suppose government is taking this thing seriously, one need to
hmm,
design courses. As per my observation, regarding quantum
yes,
computation at very basic level. So let
yeah,
us see in
and
future. Let's hope.
yeah, and yes, if you know, the AICT is developing quantum computing textbook for undergrads. I mean, those undergrads would mostly be for engineers only, as it's AICTE. AICT is developing a complete course and textbooks on uh, quantum computation for undergrads. The textbook name would be same, that quantum computing for undergrads. It would taken to that kind of level. Just I mean, whatever physics we know after 12th, that will the physics understanding would be of that level. We won't need to understand a lot of physics before going to that course.
Correct. Correct. Yeah. Okay. That's all right. Thank you. Thank you, Sangram.
Hmm. Yeah, and I hope the course would be live by next year. People
Okay.
are
Thank you.
people are already if you follow Abhay Jere, he's I guess CIO in AICT. He's vice chairman, I guess, of that innovation council. He only like announced that they are going to uh, make it make this course live by next academic year.
Yeah, but I found it to cope up with happenings in quantum computation abroad.
Hmm.
So we are lagging or
Yeah.
we are lacking. I mean, to so speed and momentum is, we need to improve in that sector.
Yes,
So the
but
time factor is very important. I mean to say,
yes.
if you compare the condition of Indian students or Indian researchers compared to abroad, so
Hmm.
we need to be very careful. We need to be very faster enough. I found this
Yes,
is
indeed.
uh,
Yeah.
yeah.
We will need to scale our resources, I mean, boost our uh, research speed, and that's the only way we can compete with the world. But it's great that we have started, and we are one of the top 10 countries who have started their quantum programs. Not even there are only less than I guess 10 countries in the world which have such quantum program, or are working towards quantum computing. So it's good thing for India.
Yeah, yeah, that's correct. That's good.
Hello,
Okay, okay.
Sangram.
Yeah, thank you.
Yes.
Hello,
Yeah. Yes.
Sangram.
Yes.
What is
Mm-hmm.
current status of quantum computing in India, and it's being
Okay.
utilized for any space mission or other significant applications?
Okay. So understand one thing, that for having for utilizing quantum computation for space missions, we would need scalable, and we would need scalable quantum hardware, right?
Yeah,
Without quantum computer chips, or without proper quantum computing infrastructure, we won't be able to do that do space missions using quantum computation. So
okay.
in 2020, government of India came up with a plan of working towards quantum satellite. Okay, but
Yeah,
then that's uh, I what I understood from the connecting the dots, that they realized that we would need to first develop our in-house quantum hardware, then only we would then only we can use in the quantum satellite. So they have like pushed that quantum satellite thing to the end of National Quantum Mission, or like later part of the, I mean, even uh, it's not kind of included in the quantum National Quantum Mission, but it's the later part of that. And I'm sure that it will be used in the space and securing the channels,
Okay. Thank you.
communication channels, basically quantum satellites would be used for securing the communication channels.
Hmm. Thank you.
Yep. Any more questions? I'm happy to take. If you have any questions, you can like write to me on mail, or you can drop me a
Hi,
link,
Sangram.
or you can
Deshpande
ask
here.
me on. Yes. Yeah.
Yeah, yeah. You said you can like we can see the
Mm-hmm.
projects, work on a project live on the
Mm-hmm.
GitHub and all. How can like
Mm-hmm.
explore those quantum computing in that side?
Okay.
How can
So
work on real life projects?
yeah.
Please.
Okay, so I guess I forgot to like mention few more links, but yeah, it was like limitation of the slides, and I could not just add a lot of content in one slide, so I didn't do that. But there are a couple of courses by Qubit. Then there are like other courses by IBM, from which you can like start learning towards quantum computing and like I would say quantum programming. Essentially, once you understand the like mathematics or algorithms, but you should implement it into uh, like some application, right? And that's what like we call as programming. And those are very nice courses by IBM. They host every year. They host summer school. It happens during July, and you can register for that. They like take you from the basics of quantum computation to the like most advanced happenings in the quantum computation within like 2 or 3 weeks time, and that could be a good start to learn, I guess.
Okay. Thank you. Thanks a lot.
Yeah, and there are like yeah, obviously there are like ample of GitHub repositories available on the quantum computation, but to understand those codes, you will need to know some basic knowledge about quantum computing. I mean, I'm saying computing, not physics or not computation, not only computers, but quantum computers or like quantum programming. So that will be given to you by these summer schools or like qubit by qubit year long online quantum school.
So we need to learn like basic codings. Is it enough to learn quantum computing, or we need to?
Yes, you would need Python for that. If you are like if you just know basics of Python, that would be even fine for you to start with quantum programming.
Okay. Okay.
Hello, sir. Good morning. Uh,
Hi. Good morning.
my name is Shiv Kumar. What is the role of quantum computing in healthcare sector?
Okay. Yeah, I mean, there are like different aspects of healthcare. So if you see drug discovery or like the like invention of drugs or invention of the medicines for one particular disease like cancers, we do not know, we do not have the cure for cancer, right? So by like simulating co the like molecular interactions using quantum computation, we would precisely know that what should be that particular protein, or what should be that vaccine, or what should be that drug we should give to that particular human, and it would like kill his disease, whatever disease. That's one of the like important application of quantum computing in the healthcare. Then there are like a couple of others that I mean I haven't touched one part in the quantum, I mean, computing. It is actually computing. Quantum would be where quantum would be um, in the like different biomedical instruments to monitor the health of that particular patient, or to make the effective usage of uh, MRI machine, and also there is another domain called as quantum machine learning. We all know machine learning, but the quantum is when like we do machine learning on quantum computation. It's called quantum machine learning, and quantum machine learning could play significant role in detecting the uh, tumors. I guess there was recent discovery that quantum computers could detect the. I mean, using quantum machine learning, some like a group of researchers have detected the um, breast cancer possibility 5 years before it happened. Like this, but we would and one of the application of quantum computation into healthcare.
Thank you, sir.
Are there any other questions? Hello,
So we
again.
have few questions in chat
Mm-hmm.
box. I
Mm-hmm.
will read.
Okay, yeah, yeah, sure.
Alpha,
Sure.
is alpha and beta also called as amplitude?
Mm-hmm. Sorry, what
Is
was the
alpha
question?
and
Yeah, the one I showed. Yeah. So those are basically amplitudes, but I haven't touched that into depth because it would be lot of maths then. But yeah, it's essentially amplitudes called as amplitude of a qubit, or in other words, when we measure that qubit, we would get that particular square of that alpha and beta is a particular of 0 to 1 qubit state. It's you can say amplitude, you can say probability of that. Both are the same thing. Or the third word, if I give it to them, that particular term is magnitude of a qubit, and that alpha plus psi, sorry, alpha psi plus beta psi was the it was expressed. It's called as a superposition of qubits. Hello, hello. Shrikant has raised his hand. So if you have any question, Shrikant, go and ask. Am I audible? Hello.
Yes, yes, you
Okay.
are audible.
Yeah. Yeah. Okay. Yeah. Shrikant, she
Hello.
go on that. Yes. Yes. Yes.
Hello, sir.
Right.
Actually, my question is regarding does this quantum
Mhm.
computing is related with DFT theory or density function theory?
Yes. I mean, it's essentially extension of DFT theory, but that's like my limitation that I do not have that physics and understanding of physics background, so I can't answer in depth on this. But yeah, DFT is used to density functional theory is used to simulate the quantum operations using mathematics. It's like theoretical quantum computation or quantum information science. It comes under quantum information theory.
So then, do you have any idea from where the basic course we used to start for this quantum computing? Means
Mhm.
at any institute from Indian government institute or from any other institute which
Okay.
gives some
Yeah.
such kind of courses.
I mean, uh, the of from IITs or from TIFR or from either like ask them that your show them your interest and ask them for summer internship, summer opportunity, or at least some remote opportunity to work on some particular project that will give you a lot of experience, expertise on the field. If you are interested in physics, then there are I guess all the ISers, you can go to any ISer professor and you can ask like, can I work with you? And if they have some project, they will definitely be happy to take you. I mean, similar thing happened to me. When I was like in, I completed my third year of engineering, and that by that time I was not having any idea that I would develop quantum computing as my career, or like I had no thought on this. I just wanted to learn, and then in the summer of third year, I approached one of the professor in ISER Kolkata. His name is Prashant Panikrehi. I mean, he was in ISER Kolkata before, so he took me as a in his lab, and I learned have 3 years. I mean, in those 3 months was, I would say, the foundation of quantum. I mean, it was my foundation to jump into quantum computing, and I guess you can uh, like follow the similar path by like asking IIT IIS's professors to like give you opportunity to work on their projects, and I'm sure they will be definitely happy to give you the opportunity if you like show that you're interested and you have some little knowledge. Not they won't expect you to have a full knowledge on quantum and all, but just little knowledge, and having interest is worth. I mean, is essential to. I mean, and it will be like fine if you have those things as well.
Okay, sir. Thank you, sir.
Yeah. Yeah. Don't be shy to work in the national quantum mission, and it will be easy for you to approach to these people, because those are be like uh, those will be like coming under one roof called as National Quantum Mission, and you can just uh, reach out to any professor you wanted. Yeah, Dr. Neetu. Yes.
Uh, yes, a very good morning, sir. Uh,
Yeah. Yes. Hello. Hello. Hi.
Actually, hi, it's really a very interesting talk. My
Okay.
question to you is that
Mhm.
recently I am working on basically I am in physics field,
Okay. Mhm.
and I am working on various government projects with the Bhabha
Mhm.
Atomic Research Center, with the Tata
Okay.
Institute of Fundamental Research on
Mhm.
photonics, and
Okay. Cool.
that are the sponsored project from these
Mhm.
agencies. Now, I wish
Yeah.
to have, being a quantum mechanics, little bit having a knowledge of quantum mechanics, I wish to
Mhm.
have some project on quantum computing with some,
Okay.
as you are telling that ISC Bangalore has some projects
Mhm.
for the
Mhm.
students. So my question
Yeah.
is, can we, as a faculty, can
Mhm.
I apply for some project with the ISC Bangalore and
Yeah.
enroll a student under that project? Could you please
Yes. 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 I
put
mean,
some light on this?
yeah, that's what like I mean, I would say that was the motivation, or that was the like that should be the ideal outcome of national quantum mission, because national quantum mission doesn't want to limit the quantum happenings till the like premier institutes in India, but they want especially like the Ajay Sood, who was like, I mean, who is, I guess, yeah, sorry, who was the chair of this National Quantum Mission Committee, was like willing to take this quantum to the like tier 3, tier 4 level colleges as well, not only the premier institutes of India. And I think you should definitely apply to, I mean, like you should definitely be in touch with the professors from IIT and ISCs, and even ISER Pune. I guess if you are in Maharashtra and like or if you are near Pune, then I would suggest you to uh, like talk to some professor from ISER Pune. They have very good I mean funding opportunities, and they support different projects, different startup ideas in quantum computing. So you would be like getting projects funding from there as well. There, ISER Pune, they call it as Innovation Quantum Innovation Hub, Quantum I Hub, I guess.
Okay.
It was
Basically,
my pleasure having you. Yeah, it was my pleasure having you in talk now.
it's my pleasure to attend this informative talk. But
Mhm.
my one question is that
Mhm.
basically I am from Punjab, and
Okay.
uh, how I can get a contact to because on the site there is no nothing. I didn't find anything regarding IIC
Mhm.
Bangalore project on quantum computing, or
Okay. Mhm.
I don't know about the
Mhm.
IISER Pune website. Is there any? But I
Yeah.
wish to ask you that could I get some contact to whom I should
Uh,
contact and
yes,
get
yes.
a
Yeah,
response?
sure, sure. Yeah. I mean, in that case, you can do one thing. You can write me an email stating like in which field you want, like you are interested to work on, and I can make you connected with the that particular field's professor or like that particular field's expert with you. I would
Right.
at least suggest you to
So
like
could you
connect with
please
that
share
particular
your
person.
mail ID
Yeah. Okay. I'll share in the text box.
in the
Okay.
chat box? Right, right.
Yeah.
Thank you.
Where is the text box? Where
Thanks.
is
Thanks for your great initiative and information. Thank you.
uh, I'm still a student. Hello.
Hello, but it's always good to talk with the
Yeah.
young generation and to learn a lot from that because
Yes.
we are a person of 70, 80s and decade, and it's always good to learn something
No,
from a
but
young
I would
generation.
say like the
बरोबर.
way you have developed things for us have really be like have really been useful for us, and the like way you have taught to us have taken us here. I would say.
Thanks for your so kind gesture.
Hmm. I'm texting my uh, Gmail on I mean my email on chat box.
Thank you. Thank you.
It was my pleasure having you in talk.
Same here.
Yeah.
Very nice talk, Sangram. I have
Hmm.
something to announce here. Uh, as Mr. Bipin Sarnavane said, we should add quantum computing in the syllabus. This year, our Wellington College Sangli has become autonomous, and we have included quantum computing in MSc first year syllabus. Though we have not much knowledge about that, we are also learning, and therefore we have planned such webinar lecture for this, and we will also grow this community. And Sangram, I have also added you in this group of quantum computing. So if you
Okay.
have anything to share, you can directly share in the
Yeah,
group.
definitely.
Yeah.
And
Uh,
I mean, I would say that rather than just having it as a course, like inspiring students to learn uh, that on their own, and like it should be better way to learn, I guess, because teachers can teach you only few things, but if a student is interested in that, he can pick one particular point, and like even quantum computing is so vast that it has multiple domains. So like I just have choose one domain, and I did only on that. That's why like I think like uh, I don't have full idea on what like a full quantum computing, but I just have like a full idea on what I'm doing and like what my domain is.
right. Yeah, so for the participants, the link is been shared in the chat box, and if you fill the feedback form, you will get the certificate of in this week, because there are a lot of activities going on. One of the activity we are conducting for the International Year of Science and Technology.
Quantum
Uh,
science.
Let me share the screen.
Mhm.
Wait a minute. So we are arranging a reels competition. So those are interested in making reels, they can you see the screen?
Yeah.
Yeah.
Yes. It's
So this is the
visible.
reels competition, and we can submit the reels on this following topics. These are topics, and I will post this also in the WhatsApp group, and the registration link will be in the chat box. So these are the competition. So we are doing very much things for this International Year of Quantum Science and Technology. So on behalf of Department of Physics, I would like to thank Mr. Sangram uh, because of his wonderful lecture. All of us in the audience, we have students as well as teachers, so I would like to thank all of them. I would also like to thank principal of Wellington College Sangli, who has supported us, and the technical team, which is helping us to smooth conduct of this webinar. Once again, I thank all the participants, and we will be in touch with the WhatsApp group. The certificates will be, you will get the certificates very soon. Thank you so much. If still you have some doubts, you can post in the WhatsApp group. I have added Mr. Sangram in this group. Yeah, the session is ended. You can leave the meeting. Thank you.
Thank you, everyone.